what particles are fundamentally made of. I mean, the standard model of particle physics is just, it's absolutely incredible.
It really is. A towering achievement, describes so much with such precision.
Exactly. 3 of the 4 forces, all the matter we know. But let's be honest, it leaves some massive questions just hanging there, doesn't it?
Oh, absolutely. Big ones, like gravity, for starters.
Right. It completely ignores gravity. And then there are all those numbers, like 19 parameters you just have to plug in from experiments.
Particle masses, force strengths.
Yeah. No explanation for why they have those values. And, nothing on dark matter or dark energy either. Big mysteries.
Huge gaps, which is, well, that's where string theory steps into the picture.
So into this void step string theory. This is a radical, incredibly ambitious proposal, really aiming for the ultimate prize. A theory of everything.
That's the ambition, yeah.
And its core revolutionary idea, the one we're diving deep into today using the source material you provided, is this. What if the fundamental building blocks aren't zero-dimensional points, but tiny, vibrating strings?
That's exactly right. And this deep dive using your source material is all about exploring the profound implications of that seemingly simple idea.
Simple idea, profound implications. I like that.
It means that those familiar properties of particles, things like mass, spin, and charge, they aren't just labels you attach to a point anymore.
Right.
Instead, they emerge entirely from the way these strings wiggle and interact, and crucially, from the environment they exist in.
So they're not fundamental in the old sense. They come from the string's behavior.
Precisely. So our mission today is to trace that path, following the source material, from just the concept of a vibrating string right through to how it could possibly explain the physical properties that define our world.
All right, mission accepted. Left part right there with that foundational shift, leaving behind the idea of points and embracing the string.
Let's do it.
So the foundational shift is replacing those zero-dimensional point particles.
The things we learn about in basic physics.
With these one-dimensional extended objects, these strings. And the source material emphasizes just how tiny we're talking here.
Oh, incredibly tiny. Almost impossible to picture.
These strings are proposed to be on the scale of the Planck length. Roughly 1035 meters.
Which is just mind-bogglingly small. Far, far beyond anything we can directly probe.
And that's why, to us, they just appear as featureless points.
Exactly. Right? They're too small to see any structure.
Now, your source highlights that there are 2 basic forms these fundamental strings can take based on their topology.
That's right. You have closed strings, which form tiny loops.
Like a rubber band?
Sort of, yeah. And open strings, which are segments with 2 endpoints, like a little piece of, string.
Okay, loop versus segment. Seems simple enough.
But this seemingly minor difference turns out to be absolutely crucial, particularly when it comes to forces. Well, the source explains that a low-energy vibration of a closed string corresponds unavoidably according to the theory's mathematics.
Unavoidably?
Yes, it's baked into the structure. It corresponds to a massless particle with spin 2.
Spin 2. Massless. That sounds familiar.
It should. This particle possesses the exact properties predicted for the graviton, the hypothetical carrier of the gravitational force.
Wow. Okay, so string theory doesn't just allow for gravity, it predicts it.
It must exist if strings do. It's one of the most celebrated results, really. Gravity just falls out naturally from closed strings vibrating in their lowest energy state.
That's pretty amazing. And you contrast that with open strings. What about them?
So the source tells us their low-energy modes correspond to spin-1 particles.
You spin one, like photons.
Exactly like photons. These are the carriers of the other fundamental forces we know. The gauge forces, electromagnetism carried by the photon. The strong and weak forces carried by gluons and WZ bosons. Those come from open strings.
Okay, so closed strings give us gravity, open strings give us the other forces. Got it. Now, unlike a point particle, which traces a one-dimensional path through space-time, it's world-line.
Right.
A string, being extended, traces a two-dimensional surface as it moves. This is called the world sheet.
That's the term, yes. Think of it like the history of the strings sweeping through time.
And the extended nature of this world sheet is actually a huge deal, isn't it? It solves a major problem.
A massive problem. It's one of string theory's greatest triumphs, conceptually at least. When you try to build a quantum theory of gravity using point particles, their interactions happen at a single sharp point in spacetime.
Like 2 points colliding exactly.
Right. And mathematically, that leads to calculations just blowing up, giving you infinite nonsensical results. It's plagued quantum gravity attempts for decades.
Okay.
But because strings are extended, their interactions, like when two strings join or one splits, don't happen at a single point. They're smoothed out, smeared over a small region on that world sheet.
So it's not an instantaneous point-like event.
Exactly. It's a more gentle process, topologically speaking, and this mechanism successfully tames those infinities. It makes the theory mathematically consistent, at least in principle, where point-particle theories failed for quantum gravity.
That's a pretty powerful fix.
It is. So let's just connect this back quickly. Closed strings, having no endpoints, are free to propagate everywhere in space-time. We often call this the bulk, which fits with gravity being this universal force that affects everything, right? It permeates the bulk.
Makes sense.
Open strings, on the other hand, have endpoints. And as we'll get into, it turns out those endpoints aren't just floating free. They get fixed to certain surfaces.
Okay. Hinting at things to come.
Exactly. And that confinement leads to more localized forces, like electromagnetism.
Okay, so that's the basic structure, how it includes gravity and other forces through different string types and their world sheets. But how does a vibrating string give rise to something like mass? In the standard model, mass is basically just, well, it's a number you measure and assign to each particle, right? Just plug it in.
Pretty much, yeah. It's an input parameter, largely unexplained why it has that value. And here's where string theory offers that first big aha moment, as the source material lays out.
Okay, I'm ready for the aha moment.
Unlike the standard model, in string theory, mass is entirely emergent.
Emergent, meaning?
Meaning it doesn't come from some intrinsic property of a point particle. It comes directly and solely from the string's vibrational energy.
So wait, the energy of the vibration is the mass?
Essentially, yes. This is a literal direct application of Einstein's famous EMC-Phe. The energy E of the string's vibration manifests as its mass.
Huh, that's neat.
It is. Think of it like the source uses a great analogy. Imagine a string on a musical instrument.
Oh yeah, a guitar string.
Right. It can vibrate in different ways and different frequencies. The energy of those vibrations determines what note you hear, the pitch.
Higher frequency, higher pitch, more energy.
Exactly. In string theory, the energy of the string's vibration determines its mass. A string vibrating gently with low energy
is perceived as a low mass particle, like an electron maybe, or a photon.
Precisely. And a string vibrating really violently with immense energy
is perceived as a very heavy particle.
That's the idea. Different vibrational patterns, like different notes or harmonics on that musical string, correspond to different particle types.
So one fundamental string, but its different notes make it appear as all the different particles.
Exactly. Each distinct vibrational pattern or mode represents a different type of elementary particle. This gives rise to an infinite tower of particles, all built from the same fundamental string.
An infinite tower. Okay.
And the lowest energy states, the ground states of vibration, the simplest wiggles, correspond to massless particles.
Like the graviton and photon we already talked about.
Exactly those. They are the lowest notes the closed and open strings can play, respectively.
Now, the source mentioned something interesting historically here. A problem with the early version, itation.
Ah, yes, an important point. The earliest version of the theory, which was purely bosonic string theory, we'll get to what that means.
Okay.
It had a serious problem. Its very lowest energy state wasn't massless, but actually had a negative mass squared.
Negative mass squared. What does that even mean?
It corresponds to a hypothetical particle called a tachyon, which travels faster than light and, more importantly, signals a deep instability in the vacuum. Basically, the theory wants to decay or collapse. It's not a stable ground state.
So a major flaw.
A showstopper, really. And resolving this troublesome tachyon was a major driver, the source notes, for developing the more sophisticated versions, like superstring theory.
Okay. And while we're using this cosmic symphony analogy, your source adds a clarification, right? About the energy scale.
Yes, it's crucial. The analogy is wonderful for visualizing different particles from modes, but we need to be careful about the energy. The tension in these fundamental strings isn't like a violin string. It's unbelievably enormous, on the order of the Planck force.
The Planck force. Unimaginably strong.
Right, so those higher harmonics, the more energetic vibrations, they don't give you familiar particles like protons or neutrons. They correspond to incredibly heavy, exotic particles with masses approaching the Planck mass, vastly heavier than anything we've ever observed.
So we wouldn't see those higher harmonics directly.
Not with current technology, no. But importantly, the source explains that this predicted infinite tower of super heavy particles isn't actually a problem for the theory, it's a crucial feature.
How can an infinite number of unobserved heavy particles be a good thing?
Because, mathematically, these massive states contribute to the quantum calculations in precisely the right way to cancel out other potential infinities, the ones that can still pop up even with the smoothed-out interactions. They're essential for making it a truly consistent, finite theory of quantum gravity.
Huh. So the unseen heavy particles are needed to make the math work for the particles we do see.
That's subtle.
It's part of the intricate self-consistency of the theory. Fascinating. Okay, so mass is fundamentally tied to the string's energy of vibration. What about spin? Spin is that purely quantum mechanical property, right? Intrinsic angular momentum.
That's right. And it classifies particles into two big families: bosons with integer spin, 0, 1, 2, and fermions with half-integer spin, 12, 32.
Force carriers versus matter particles, roughly speaking. How does that emerge from a string?
Spin, too, emerges from the string's quantum behavior. Specifically, the source tells us it comes from the quantization of the string's various motion modes.
Motion modes, not just vibration.
Right. It includes the vibrations we talked about for mass, but also incorporates a kind of quantum rotation on its world sheet. Quantization, remember, is that core quantum idea where properties like energy or angular momentum can only take on specific discrete values.
Okay, so quantizing the string's motion.
Exactly. But the source points out a big issue with that early bosonic string theory we mentioned before.
The one with the tachyon.
That's the one. It only produced particles with integer spin bosons, like the photon and graviton. It completely lacked the half-integer spin particles, the fermions, things like electrons, quarks, neutrinos, the very stuff matter is made of.
Right, that's kind of a big omission for a theory of everything. You need matter.
Precisely. This was a critical failure. You can't build the universe we see without fermions.
So how did they fix that? How do you get fermions out of strings?
The key resolution, as described in your source material, came from what's often called the first superstring revolution. The breakthrough was the introduction of supersymmetry, or CUEY.
Supersymmetry. I've heard of that. It relates bosons and fermions somehow.
It does. Supersymmetry is this theoretical principle that postulates a deep underlying symmetry between bosons and fermions. It suggests that for every boson particle type, there's a corresponding fermion partner, a superpartner, and vice versa.
Okay, so how do you add CUEY to a string?
In string theory, you incorporate CUEY mathematically by adding new entities onto the string's world sheet. Alongside the familiar bosonic fields that describe the string's position in space-time, like X, you introduce new fermionic fields, often denoted company. These are fundamentally different mathematical objects. They live on the world sheet too, but they have a special property involving anti-commuting numbers.
Anti-commuting numbers. Sounds complicated.
It's a bit technical, but the source explains that this property is actually the deep origin of the Pauli exclusion principle for the resulting fermions in space-time.
The rule that says no two identical fermions can be in the same place at the same time.
Exactly that rule. It comes from the fundamental nature of these fermionic fields on the world sheet.
Wow. Okay, so adding these fermionic fields is the key. How does that actually give you fermion particles?
Well, in the commonly used mathematical framework, the source mentions the Ramond-Neveu-Schwarz, or RNS formulation. It comes down to the boundary conditions you impose on these new fermionic fields as they move around the string.
Boundary conditions. Like what happens at the ends or as you go around a loop.
Exactly. If you're looking at a closed string loop, you can demand that the fermionic fields come back to themselves either the same way, periodic, or with a minus sign, antiperiodic, after going around the loop.
Okay.
It turns out if the fields obey antiperiodic boundary conditions, this is called the Neveu-Schwarz or NS sector, the resulting quantum states, the particles, are space-time bosons with integer spin.
So the NS sector gives bosons. What about the other one?
If they obey periodic boundary conditions, that's the Ramond or R sector, the resulting states are space-time fermions with half-integer spin.
Ah. So the choice of boundary condition on these world sheet fields determines whether the string represents a boson or a fermion in our space-time.
That's the core idea in the RNS picture, yes.
Oh.
There's also a technical step mentioned in the source called the GSO projection. It's a consistency requirement.
What does that do?
It does two crucial things. It reliably gets rid of that problematic tachyon state we talked about earlier, both in the NS and R sectors. And, importantly, it ensures there's an equal number of bosonic and fermionic degrees of freedom at each mass level, which is a requirement for a consistent supersymmetric theory.
So it cleans things up and balances the books between bosons and fermions.
You could put it that way, yes.
Huh?
So the takeaway here, drawing from the source, is that spin in string theory isn't just one thing. It's a composite property.
A composite.
Yeah, it arises from quantizing different types of excitations on the string's world sheet, the original bosonic ones related to position, plus these new fermionic ones introduced by supersymmetry. The different quantum rules for these two types of excitations lead naturally to either integer or half-integer total spin for the resulting particle.
So a single underlying superstring, depending on how it's excited quantum mechanically,
Can manifest as either a boson or a fermion. It unifies force and matter particles in a fundamental way.
Okay, that covers mass from vibration energy and spin from quantum motion modes plus supersymmetry. That leaves charge. Where does something like electric charge or the color charge of quarks come from in this picture? You mentioned the graviton from closed strings is neutral.
Right, and that's a key point. Closed strings, like the graviton, don't naturally carry the kinds of charges associated with gauge forces like electromagnetism. For that, we need open strings.
Okay, back to the open strings.
And this brings us to another key aha moment, one tied to a major discovery from what's called the second superstring revolution in the mid-90s, D-branes.
D-branes, I've heard that term. What are they?
Your source explains that, unlike closed strings, which roam freely in the bulk spacetime, open strings have endpoints. And it turns out, for mathematical consistency, these endpoints aren't just free to flap around anywhere. They must be attached or end on specific surfaces embedded within the higher dimensional spacetime.
Attached to surfaces, like stuck.
Essentially, yes. These surfaces are called DP-branes, or Dirichlet branes. The P indicates their spatial dimension, so a D0 brane is a point, a D1 brane is a line or a string itself, a D2 brane is a membrane, a D3 brane is a three-dimensional volume, and so on, up to D-branes that could fill all the spatial dimensions.
So space-time in string theory isn't just empty space. It has these brain structures embedded in it.
Exactly. It's part of the necessary furniture of space-time if you have open strings.
And the source even briefly mentions that wild idea, the brain world scenario.
It does. It's this intriguing possibility that maybe our entire observable universe, everything we see, all the standard model particles and forces which arise from open strings, is confined to exist on a three-dimensional D-brane, a D3 brane.
Like we're living on a sheet within a higher dimensional space.
Sort of, yeah. And in this picture, only gravity, mediated by closed strings, would be free to propagate into the larger, higher dimensional space, the bulk.
Which could explain why gravity seems so much weaker than the other forces, because it's diluted across more dimensions.
That's one of the main motivations for brain world models, yes. It's a fascinating possibility, though still speculative.
Okay, but back to charge specifically. How do D-branes give rise to charge?
The key insight, explained in the source, is that you can assign mathematical labels, often called Chan-Paton factors, to the endpoints of the open strings. These labels essentially act like little tags telling you which D-brane the string starts on and which D-brane it ends on.
So a string can stretch between two different D-branes.
It can, if they're close enough or overlapping,
Sure.
or it can start and end on the same D-brane.
And these labels, they relate to charge.
They are the origin of charge. This labeling scheme provides a beautiful geometric origin for the gauge theories that describe forces like electromagnetism and the nuclear forces.
Geometric origin. How?
Okay, take the simplest case. Just a single D-brane. An open string starts and ends on this same brane. Let's label this brane I, so it's an I string. The source shows this configuration naturally gives rise, at low energies, to a U1 gauge theory.
That's the mathematical structure of electromagnetism, right?
Exactly, and the massless spin-1 particle arising from the vibration of this II string is identified as the photon.
So the photon is just an open string tied to a D-brane. What about more complex forces?
Now imagine you have a stack of n identical D-branes sitting right on top of each other. Strings can now stretch not just from a brane to itself, like IIJJ, but also from one brane to a different brane in the stack, like IJ, where I is not equal to J.
Okay.
The source explains that this setup, with strings stretching between different branes, naturally gives rise to a richer, non-abelian UN gauge theory.
UN, like the SU3 of the strong force or the SU2 of the weak force.
Precisely. Those are related subgroups. The strings stretching between different branes in the stack literally carry the charge associated with that force. Their endpoints being on different branes is what gives them the charge.
So charge isn't some intrinsic property of the string substance itself.
Correct. It's a relational property. It's defined by which D-branes the string's endpoints are connected to. It's all about the string acting as a connection between these geometric objects, the D-branes.
That's a completely different way of thinking about charge. It's not something a particle has. It's about where its string ends.
Exactly. And the source goes on to discuss this idea of geometric engineering.
Geometric here.
Yeah, the idea is that by choosing specific, perhaps complicated configurations of D-brane stacks, how many branes, how they intersect, maybe wrapping them around cycles and extra dimensions.
Oh, okay.
You can, in principle, reproduce the precise gauge group of the standard model. SU3 for the strong force, SU2 for the weak force, and U1 for electromagnetism.
So you could build the standard model forces just by arranging branes correctly.
That's the hope. The source gives an example. Remember the 3 colors of quarks in the strong force, SU3.
Yeah.
In this picture, those 3 colors could literally correspond to which of 3 stacked D-branes the quark's open string endpoint is attached to.
Mind blown. Okay. So fundamental questions in particle physics like, why do we have these specific forces, or why do quarks have 3 colors? They transform into questions about string geometry.
Exactly. They become why this particular configuration of D-branes, or what determines the geometry of these branes. It shifts the origin of these properties from arbitrary labels to the structure of space-time itself.
It's a really profound shift in perspective. Okay, now we absolutely have to talk about the elephant in the room, or maybe the tiny curled-up elephant in every point of space. Extra spatial dimensions.
Right. Can't talk string theory without talking extra dimensions.
Your source material is unequivocal. String theory requires additional spatial dimensions beyond the 4 we experience, 3 spatial, 1 time.
It does. For mathematical consistency, particularly for superstring theories to work and cancel anomalies, they don't live in 4 space-time dimensions. They naturally live in 10.
10 dimensions, 6 more than we see. So,
where are they? Well, the proposed solution, the standard answer, is compactification.
Compactification, making them small.
Exactly. The source explains this using the classic analogy. Imagine looking at a garden hose from a very far distance.
Okay, it looks like a one-dimensional line.
Right. But as you get closer, you realize it has another dimension, a small, curled-up dimension, its circumference.
Ah, I see.
So the idea in string theory is that those extra 6 spatial dimensions are curled up, or compactified, into a tiny complex shape at every single point in our familiar 4D space-time.
Curled up everywhere.
Everywhere. But they're hypothesized to be incredibly small, maybe near the Planck length again, so small that we just don't perceive them in our everyday lives or even in our most powerful experiments.
Okay, so they're hidden because they're tiny.
Yeah.
But does the shape of these hidden dimensions matter?
Oh, absolutely critically. This is where the geometry of these curled-up spaces becomes central to connecting string theory back to the physics we do see. The source emphasizes this strongly.
How does the shape affect our physics?
Well, for the theory to produce a 4D world that looks like ours specifically, one that has the right kind of particle physics, maybe preserving some amount of supersymmetry down to lower energies, these 6 compact dimensions can't just be curled up any old way. They must have a very special kind of geometry.
It's special shape.
Yes. The source points to a class of complex mathematical shapes known as Calabi-Yau manifolds as the leading candidates. These are intricate, 6-dimensional spaces with specific mathematical properties.
Calabi-Yau manifolds. Okay. And what's so profound about them?
What's truly profound here is the geometry to physics dictionary that the source describes. It's not just a loose connection. The specific shape and topology, the fundamental structure of this tiny, unseen Calabi-Yau space, is believed to directly determine the properties of the particles and forces we observe in our large dimensions.
Directly determined. Give me an example.
Okay, so the source explains there are 2 main ways this works. First, the topology of the Calabi-Yau manifold fundamental structural features, like the number of holes it has in different dimensions.
Topology, like whether it's a sphere or a donut.
Kind of like that, yes, but much more complex in 6D. This topology determines discrete properties of the particle spectrum. For instance, the number of families or generations of fundamental particles we see in the standard model.
Like the electron-muon-tau families.
Uh,
There are 3 of them.
Exactly 3. A Calabi-Yau manifold with the right topology can naturally predict exactly 3 generations of particles. It comes from the topological numbers of the manifold.
Wow. So the number 3 isn't arbitrary. It's counting holes in a hidden space.
That's the idea. Second, the specific geometry of the manifold, its precise size, the angles between its curves, its overall shape, often parameterized by things called moduli.
Okay, the detailed shape, not just the basic structure.
Right. This detailed geometry determines the continuous parameters of our world. Things like the exact masses of the particles and the strengths of the forces, the coupling constants.
How does the shape set the mass of an electron, say?
Your source gives a great example related to this. Particle masses and how strongly they interact, like the Yukawa couplings related to the Higgs mechanism, are calculated based on how the wave functions of the corresponding strings overlap within this tiny Calabi-Yau space.
Wave functions, like the quantum probability clouds.
Exactly. Imagine the shape of the Calabi-Yau forces the wave functions of 2 particles that could interact to be mostly located in different regions of that tiny space. Their overlap integral will be small.
So they don't see each other very well.
Right. And that translates into a weak interaction strength, or a small resulting mass from that interaction. If the geometry allows their wave functions to overlap significantly,
The interaction is strong, or the mass is larger.
precisely, it provides a geometric mechanism for generating the hierarchies of masses and couplings we observe.
It's an incredible idea.
Yeah.
It means these fundamental physics questions that are just mysteries in the standard model become geometry problems.
That's the promise.
Like, why are there exactly 3 generations of particles becomes, what's the topology of the compact space? And why is the top quark so much heavier than the electron? Becomes, what are the specific size and shape parameters of the curled up dimensions, and how do the relevant particle wave functions overlap within them?
That's the translation, yes. In principle, all those 19 arbitrary numbers we currently plug into the standard model could be derived, calculated, from the geometry and topology of this hidden space.
That vision sounds incredibly complete and, well, beautiful, elegant.
Nothing elegant.
But the source is also very clear about the significant challenges string theory faces, the things that prevent it from being, experimentally proven science right now.
Absolutely. We have to be realistic. Your source material details these hurdles quite well. Perhaps the most significant conceptual challenge is what's known as the landscape problem.
The landscape sounds vast.
It is vast. The issue is that the mathematical consistency of string theory doesn't seem to pick out just one way to compactify those extra dimensions, or just one configuration of D-branes, or one way to set other parameters like background fields called fluxes.
There are many possibilities.
An absolutely enormous number. Each distinct, self-consistent configuration corresponds to a different possible vacuum state, effectively, a different possible universe with potentially different particles, different forces, different physical laws.
How many possibilities are we talking?
The numbers are astronomical. Estimates from the source often cite figures like men under 500, maybe even vastly more, consistent solutions, or vacua. It's a landscape of possibilities.
10 to the 500.
Yeah.
That's more than the number of atoms in the observable universe by a huge margin.
Exactly. It's unimaginably large. And the core issue here is prediction.
Right. If the theory allows for basically anything, how do you predict our specific universe?
That's the problem. It seems string theory can accommodate the standard model and our observed physics, yes, but it seems it could accommodate almost any other set of physical laws, too. This makes it incredibly difficult, maybe impossible, to make a unique falsifiable prediction that could definitively prove or disprove the theory.
So it explains everything and therefore nothing specific.
That's the harsh criticism you sometimes hear, yeah. The source notes the critique that because of this flexibility, it might be not even wrong, meaning it's so adaptable it can't be meaningfully tested against experiment.
And the source briefly mentions the anthropic principle connection here.
It does. That's one controversial response to the landscape. The argument is, well, maybe all these universes exist somewhere, perhaps in a multiverse, and we simply find ourselves in one with the specific laws and parameters that allow complex structures, stars, planets, and ultimately conscious observers like us to evolve.
Because if the laws were different, we wouldn't be here to ask the question.
Right. But, as you can imagine, many physicists find that explanation deeply unsatisfying as a fundamental scientific prediction. It feels more like a statement of selection bias than a predictive theory.
Okay, so the landscape is a huge theoretical challenge. What about experiments?
Right. Beyond the landscape, there is the immense practical challenge of experimental verification.
The energy scales, right?
Yeah, exactly. The fundamental energy scale associated with the strings themselves, and likely the scale of compactification, is expected to be near the Planck energy. That's about 1019 GeV.
And the LHC, our most powerful collider.
Operates around 104 Drang. That's
Yeah.
a difference of 15 orders of magnitude. It's like comparing the size of a bacterium to the size of the entire solar system.
So directly observing strings or probing the extra dimensions if they're Planck-sized is just completely out of reach.
Completely out of reach for the foreseeable future, yes. Maybe forever, practically speaking.
So we rely on indirect searches, looking for consequences at lower energies.
That's the hope. But the source mentions that indirect searches so far haven't provided confirmation either.
Like supersymmetry. You said COI was key.
Yes, many simple models inspired by string theory predicted that supersymmetric partner particles should appear at energies accessible by the LHC. But despite years of extensive searching,
Nothing.
no definitive sign of them. That doesn't kill string theory, partners could be heavier, but it ruled out the simplest, most hoped-for scenarios.
What else? Any other indirect signs looked for?
People have looked for evidence of large extra dimensions, ones that might be significantly bigger than the Planck length, though still microscopic. Those searches have also yielded null results, and any connections to cosmology, like specific patterns in the cosmic microwave background predicted by certain string models, remain highly speculative and unconfirmed.
So, theoretically challenging with the landscape, experimentally challenging with the energy scales. Where does that leave string theory research now?
Well, it's led to a shift in focus for some researchers towards what your source highlights as the swampland program.
The swampland sounds ominous, related to the landscape.
It is. The idea is, okay, maybe the landscape of 100 and 500 solutions isn't entirely legitimate. Maybe many of those mathematically consistent-looking theories can't actually be realized in a true, consistent theory of quantum gravity that includes things like black holes evaporating correctly.
So some parts of the landscape are swampy, not solid ground.
That's the metaphor, yes. The goal of the swampland program is to try and identify general principles, universal constraints, that any consistent theory of quantum gravity must obey, regardless of whether it's string theory or something else.
Trying to find the rules of the quantum gravity game.
Exactly. Theories that violate these principles are hypothesized to reside in the swampland, meaning they look okay mathematically, maybe, but they're somehow inconsistent or can't be connected to a well-behaved UV completion like string theory.
Are there examples of these principles?
Yes. Researchers formulate various swampland conjectures. The source might mention things like the weak gravity conjecture, which posits that gravity must always be the weakest force in any consistent theory, or conjectures about the allowed range of certain parameters.
And the hope is that these conjectures, if true, could rule out huge portions of the landscape.
That's the hope. By mapping the boundaries between the valid landscape and the forbidden swampland, physicists aim to drastically narrow down the number of viable string vacua, potentially restoring some predictive power to the theory. It's an active area of research.
Interesting. And the source also points out that even with all these challenges in connecting directly to our universe,
Yes.
the mathematical machinery developed for string theory has been incredibly useful elsewhere in physics.
Oh, immensely so. That's undeniable. Concepts and techniques originating in string theory, like the AD-CFT correspondence or duality symmetries, have provided powerful new tools and profound insights into other areas.
Like what?
Things like strongly coupled quantum field theories, understanding the behavior of quarks and gluons inside protons, for example, or describing exotic phases of matter in condensed matter physics, even aspects of black hole physics. The mathematical framework is incredibly rich and continues to yield unexpected connections.
So even if it's not the final theory of everything for our universe, its development has spurred a lot of progress.
Without a doubt. Its influence on theoretical physics over the last few decades has been enormous.
Okay, so let's try and quickly recap this deep dive, drawing from your source material. String theory makes this profound proposal. Ditch the zero-dimensional point particles.
Replace them with tiny, vibrating, one-dimensional strings.
Right, and from this simple-sounding premise, a whole new picture emerges where fundamental particle properties aren't just given, They're emergent phenomena.
Exactly. Mass comes directly from the energy of the string's vibration, thanks to Eames behalf.
Spin arises from the quantum mechanical behavior and the different excitation modes of the string, crucially needing supersymmetry to incorporate both integer spin bosons and half-integer spin fermions.
Correct. Force carriers and matter particles from the same string.
And charge. Charge comes from the geometry of space-time itself, specifically. The fact that open string endpoints have to attach to these higher dimensional surfaces called D-branes.
Providing a geometric origin for gauge forces, yeah. Where the string ends determines its charge.
It's a framework with immense conceptual power, isn't it? Promising to unify all fundamental forces, including gravity, with matter particles.
And potentially explaining all those mysterious parameters of the standard model, the masses, the couplings, the family structure, through this specific geometry and topology of unseen, curled-up extra dimensions.
It's a grand vision.
It is. But, as your source material makes very clear, for all its mathematical elegance and explanatory potential, string theory remains, for now, a speculative framework.
Not yet experimentally proven.
Not yet, no. The vast gap in energy scales between the predicted string phenomena and our current experimental reach is a huge hurdle for direct verification.
And the landscape problem.
And the sheer number of possible universes seemingly allowed by the theory of the landscape problem seriously challenges its ability to make unique, testable predictions about our specific reality. Though, as we discussed, the Swampland program is actively trying to address this to constrain the possibilities.
So it remains this beautiful, compelling vision, but its concrete connection to the universe we actually live in is still, well, it's still an open question, subject to intense research and debate.
That sums it up well. An ongoing quest.
Well, thank you for bringing us the source material for this deep dive. It's a complex, but truly awe-inspiring topic to explore.
It certainly stretches the mind.
It really does. And maybe a final thought for you, our listener, to ponder, building on what we've discussed from the sources. As you go about your day, just hold on to this idea for a moment. Think about how, in theory, the unseen intricate geometry of tiny curled-up dimensions, far smaller than anything we could possibly probe, could be the hidden blueprint, the underlying pattern that actually determines the fundamental rules, the particles, the forces you interact with every single second of every single day. It really makes you wonder, doesn't it? How much of the reality we experience is actually shaped by a hidden world we can't yet perceive?